We're going to be learning how to graph quadratic functions in two different forms. Today we're specifically going to look at graphing quadratics in standard form. Standard form is the form that everyone should be used to. It's the form that we used all of the last unit, or for all of the last unit. Standard form is in the form of ax squared plus bx plus c. So when we graph quadratic functions, we're graphing the shape of a parabola, and it looks like a U. We're going to use the vertex and the axis of symmetry to achieve this graph. We're going to use those two values to identify obviously where the vertex is, but also where the center of the parabola is, which we will use as a reflection line. Right here, the axis of symmetry is found by an equation, x equals negative b over 2a. That gives you the line for the axis of symmetry. Okay, that gives you the equation for this line right here. And when I graph these functions, I like to graph that line as a dashed line because it's not actually part of my graph. It's just a line we use to help us achieve the graph. So for the first example, I have typed out all the steps you should follow in the correct order that you should follow them. Number 1, we have x squared minus 4x minus 5. The first step is to find the axis of symmetry using this equation. In the above equation, we have x squared minus 4x minus 5. I'm going to identify my a value as 1, my b value as negative 4, and my c value as negative 5. And then I'm going to substitute whichever of these values I need to into the axis of symmetry equation. X is equal to negative b, which is negative 4, divided by 2 multiplied by 1. If I simplify this, I have positive 4 in the numerator and positive 2 in the denominator, which simplifies to a value of 2. This tells us that x is equal to 2. This is called the axis of symmetry. I'm going to abbreviate that as AOS. I'm also going to graph this line in the coordinate plane. I'm going to graph it as a dashed line. It's going to occur at x equals 2. That would be this line here. I'm also just going to take a second and label it. That way when I look back at my graph, I can see every part. Okay, now that we found the axis of symmetry, we need to find the vertex. And the vertex is found by substituting the axis of symmetry, the x value of the axis of symmetry, back into the original equation and solving for y. Knowing that we need to substitute the axis of symmetry, in this example it's specifically x equals 2, back into the original equation and solve for y, I'm just going to rewrite the original equation. That would be this one here. That way we have it right in front of us. y equals x squared minus 4x minus 5. Okay, I'm going to replace all x values with my value of 2. Y equals 2 squared minus 4 times 2 minus 5. And again, I just replaced x with 2. Two squared is 4. 4 times 2 is negative 8 minus 5. 4 minus 8 is negative 4. Minus 5 again is negative 9. That tells us that y is equal to negative 9. Okay, if x equals 2 and y is equal to negative 9, I can write my vertex as an ordered pair, which is 2, comma, negative 9. I'm going to plot this graph, this point on the graph in blue. And I'm also going to label it as my vertex. The x-coordinate of the vertex is always the same as the axis of symmetry. If it wasn't like that, then this point would not be on my dashed green line. So again, it always has to be the same as the axis of symmetry. The next step in graphing for standard form is to find the y-intercept. And to find the y-intercept, you need to substitute x equals 0 back into the original equation and solve for y. Our original equation is y equals x squared minus 4x minus 5. If I substitute x equals 0 back into this equation, we end up with 0 squared minus 4 times 0 minus 5. 0 squared is 0, 4 times 0 is 0, and we are left with y equals negative 5. So for this example, our y-intercept happens at 0 for the x-coordinate, y-coordinate negative 5. Zero, negative 5 is right here on the graph. We're going to label that as our y-intercept. Next, we need to find one more point on the same side of the axis of symmetry as the y-intercept. So using my highlighter, I'm going to indicate what I'm talking about here. Here's our axis of symmetry. And in my directions that I just highlighted in yellow, it says find one more point on the same side of the axis of symmetry as the y-intercept. So the y-intercept is on this side of the axis of symmetry. I need to find one more point on that side, the side that I just shaded in yellow. I'm going to erase the yellow, so you don't need to do that on your paper. I'm just indicating which side we're looking at. Here is my y-intercept. So I need to pick a point close to that. I always pick x values that are either 1 point to the left or 1 point to the right, depending on which side of your axis of symmetry you're working with. So because I'm trying to find a point in my yellow shaded region here, I'm going to test a point at x equals 1. So right at that value, or right here at this orange line. Of course, that's not going to be where the point is, but that's just going to be the x value that I test. So if I could make any suggestion, just pick a point as close to the axis of symmetry and y-intercept that you can. We're going to test when x equals 1. Our original equation is y equals, we have x squared minus 4x minus 5. I'm going to replace all x values with the new point of x equals 1. 1 squared minus 4 times 1 minus 5. We end up with 1 minus 4 minus 5. 1 minus 4 is negative 3. Negative 3 minus 5 is negative 8. Y equals negative 8. So my extra point occurs at 1 for an x value, negative 8 for a y value. When I plot this point on my coordinate plane, this point is right here. Now I could have tested other points. Just again, make sure you're picking a point that is close to that axis of symmetry and y-intercept. And the last part about graphing is this note down here at the bottom. So it says, graph the axis of symmetry, the vertex, the y-intercept, and the extra point on the same coordinate plane. Then, this is the important part, then reflect the graphed points over the axis of symmetry to create 2 more points and sketch the graph. Looking at my y-intercept, if this point is 2 units away from the axis of symmetry, then I'm going to move 2 units in the other direction and graph the reflection. If this point is 1 unit from the axis of symmetry, I'm going to move 1 unit in the other direction and graph the reflection. Once you have these points graphed, you should have a total of 5 points. 1, 2, 3, 4, 5 points. Now you can sketch your curve. So we know it's going to be U-shaped. It's going to come down, it's going to touch all points and head back in the same direction. Do your best to sketch the curve. It's probably not going to be perfect. That's okay, it's just a sketch. But that is your final answer. For example set 2, I'd like everyone to change this equation. The one I gave you, this one here, negative 5x squared minus 10x plus 6, doesn't fit on the graph. So if we change it, we'll make something fit right to the graph. Let's change this and graph the equation y equals negative 2x squared plus 4x minus 1. And from this problem, we can identify our a value as negative 2, our b value as 4, and our c value as negative 1. We're going to start with step A, which was the axis of symmetry. And the axis of symmetry is found by the equation negative b divided by 2 times a. Here our a value is 2 and our b value is 4. When we substitute our values into the equation, we have negative 4 divided by 2 times negative 2. This simplifies to negative 4 divided by negative 4, or positive 1. So our axis of symmetry occurs at the line x equals 1. Okay, after we find the axis of symmetry, the second step was to find the vertex, and the vertex is found by substituting our x value back into the original equation and solving for y. Our original equation is y equals negative 2 times x squared plus 4 times x minus 1. And we're going to substitute in the fact that x is equal to 1. Because we found that the value of y is 1, we know the vertex has an x value of 1 and a y value of 1, so we can plot the vertex at 1, 1. The next step is to find the y-intercept. And to find the y-intercept, you substitute x equals 0 into the original equation, which is negative 2x squared plus 4x minus 1. When we substitute 0 into this, we have negative 2 times 0 squared plus 4 times 0 minus 1. This is equal to negative 1. So when the x-coordinate is 0, the y-coordinate is negative 1. This here is your y-intercept. We can plot that point on our graph. And now the last step for graphing is to find one additional point. And you always want to pick a point on the same side of the axis of symmetry as your y-intercept. Here's the y-intercept, so we need to pick a point close to that. Because the y-intercept occurs at 0, I think I'm going to test a point at negative 1. So we know the point's going to be somewhere over here, but we need to calculate exactly where it's going to be. So we're testing this at x equals negative 1. When we substitute that into the original equation, we have negative 2 times negative 1 squared plus 4 times negative 1 minus 1. Simplify this, we have negative 2 times 1 minus 4 minus 1. That would be negative 2 minus 4, which is negative 6, minus 1, which is negative 7. Our additional point occurs at negative 1, negative 7. Okay, once we have our vertex, our y-intercept, and our additional point graphed, we can now reflect our y-intercept across the axis of symmetry, and we can also reflect our additional point across the axis of symmetry. After you have those 2 points graphed, you can sketch your curve, which should appear to be in the shape of a U, and in this case it is opening down. This is your final graph with 5 points on it. So in previous years that we've been in school, we've talked about this together. So it says, why is it important to find additional points before graphing a quadratic function? And what we usually come up with is something along the lines of the fact that additional points make the sketch more accurate. Without the additional points, the shape would be unclear. So if we didn't have these extra points right here on our graph, we might be slightly guessing where the bottom of that curve is going to be. By having those extra points, we are clearly seeing where we need to graph. So the importance of the additional points is just for accuracy. Okay, the minimum and maximum value, we did talk about this on the last note sheet. We talked about when the graph opens up, it has a minimum value because it has a low point. And when the graph opens down, it has a maximum value because it has a high point. Today, we're just going to re-talk about that or kind of go over that again and how to apply it to a function without seeing a graph. So if the graph opens up and has a minimum value, then the a value of your graph is going to be greater than 0. When the graph opens down and has a maximum value, your a value is going to be less than 0. For the last example set, we have problems that deal with the maximum and minimum values of the function. Number 1 says to determine whether the function has a minimum or maximum value, state the minimum or maximum value, and state the domain and the range of the function. So nowhere in here do I ask you to graph. I'm just asking you to use what you know about the functions, but what you also know about graphing to answer those questions. So let's start with part A, which is determining whether the function has a min or a max value. That's what we just went over in the above box. So we determined that if the a value is greater than 0, it's going to have a minimum. And if the a value is less than 0, it's going to have a maximum. So in this case, we are specifically looking at our a value. Here we have an a value of -4. So if we have an a value of -4, that's less than 0, and that's telling us that the graph is opening down and therefore has a maximum. That's all that part A is asking us to do. State whether we have a min or a max. Part B is asking us to determine what that value would be. So knowing that we have a maximum value because you can only have one of them, we now need to find what that value is. And the maximum value is the y-coordinate of the vertex. So we need to actually calculate what the vertex is, and then we need to identify the y-coordinate. So in order to calculate the vertex of this equation, we need to first find our x value, which is known as our axis of symmetry. And that's found by -b over 2 times a. If I substitute my values in here, I have -12 divided by 2 times -4. This is -12 divided by -8. This does simplify to a fraction. It's going to simplify to x equals 3 over 2. 4 goes into 12 3 times. 4 goes into 8 twice. Because we have a negative in the numerator and the denominator, it simplifies to a positive value. Now that we found the x-coordinate, we need to substitute that back into the original equation and solve for y. The original equation is f of x is equal to -4 times x squared plus 12 times x plus 18. So wherever I see x, I am going to replace it with the fraction of 3 over 2. I will say that this one is a little more challenging because of the fraction. We won't see many that are fractions, but it is a good idea to see a few of them. That way, if you get one with a fraction, you're not completely shocked. All right, so I replaced all values of x with my fraction. And next I'm just going to work on simplifying this. I have -4. 3 over 2 squared is the same thing as 9 over 4 plus 12 times 3 over 2 plus 18. When I multiply -4 times 9 over 4, the 4's can cancel, leaving us with just -9. 12 times 3 over 2, 2 goes into 12 6 times. I'm left with 6 times 3, which is positive 18, plus 18. When I add -9 plus 18 plus 18, that simplifies to 27. Now I know that my vertex occurs at x value 3 over 2, y value 27. Because I just solved for the vertex, I also know that my maximum value is this y-coordinate. So to answer part B, my max value is at 27. All right, and lastly, I'm going to do part C. So part C asks us to find the domain and range. This is kind of just whether or not you can utilize all parts of the graph that we've been talking about, or if you can't, then you just need to sketch a quick curve, which is completely fine. So we know that this graph opens down. We already determined that in part A. We know that it has a maximum value. And in part B, we determined the vertex, which is at 3/2, 27. So the vertex is somewhere up here, and this graph is opening down. So in order to determine the domain of this function, hopefully you can see that it goes on forever, so it's from negative to positive infinity. And the range is going to be from negative infinity until the y-coordinate of 27. So in part A, we determined that we had a maximum value. In part B, we calculated the vertex, and the y-coordinate of the vertex is your maximum value. And then in part C, we just utilized everything we know about graphing and the vertex, and we determined that our domain is from negative to positive infinity, and the range is from negative infinity to 27. Okay, for the last problem, I'm just going to work through this. You guys can follow along with my work. I would say that number 2 is definitely easier than number 1 because you do not end up with a fraction. Number 2 is more like what you'll see on your practice assignments or on a quiz.